Welcome back. In this video, we're going to be discussing shaft design, basically how we specify and spec out all the components or the parameters related to a shaft component. But before we start, we need to talk a little bit about terminology. So a shaft is a rotating element that carries power or rotation or motion to our or between components. Whereas an axle is commonly referred to as a stationary component, so it is non-rotating. Obviously, the axle in your car is actually a rotating element, but that's a holdover from wagon wheels days when the wagon wheels rotated about the axle. So these will become important in terms of considerations for lots of things. So typically axles experience a lot more static failure, whereas the shaft will experience both fatigue and static failure. So we're going to focus more on shafts in this class, but it also relates to other components. So say if the bearings, for example, we'll be curious whether the inside or the outside of our bearings, whether it's the inner raceway or the outer raceway that's rotating. So if you have a solid axle, a non-rotating axle, and something spins about it, that tells you that it's the outside raceway that's spinning. Whereas if you have a shaft rotating, then typically it's the shaft being supported by those bearings, and so it's the inner raceway that's moving. So depending on what you're dealing with, you may have different concerns, but we're going to focus on shafts. And specifically, we have a couple goals, and they are avoiding the ways that a shaft can fail. So our goal is to avoid static failure, fatigue failure, and any sort of significant deflection. So the ways that we are concerned of the shaft are typically that the shaft itself won't break, it won't yield and be plastically deformed, it won't grow cracks over time, which is the fatigue dynamic failure, as well as it won't warp so much even within the elastic region that it's not useful to us. So we care about things like how much it's deflecting, what the angles of twists are, as well as avoiding those natural frequencies. So we have a strategy to do it, and our three-part strategy in the order is going to be materials, layout, and geometry. So let's begin with the materials side. So our approach to designing shafts, we have a couple parameters that we can change, and it makes sense to start with materials because as we go through this process, you'll see that there are quite a few variables that depend on material properties such as strength and modulus of elasticity, shear modulus. So it becomes a little bit difficult to given all these things, find a material because there's too many variables that depend on material. So that's why it's a little bit easier to start with choosing a baseline material, such as choosing a low carbon steel that we can get pretty cheaply, and then have a basis of cost based on that starting steel. So if we need to go up in price for either a higher performance material, we can adjust it based on that, so the unit cost. So we're making trade-offs in terms of strength, the diameter that that using that material would require us to use. So, if your strength is too low or your diameter is too big, then you can choose a higher strength material. So not all materials can be used in all situations. So for example, if you have diameters less than about 3 inches or 75 millimeters, then you can use cold drawn steel. But if you're higher, you're going to need to use a hot rolled. You can't really easily get larger diameters in a cold drawn rope. So you need to use hot rolled for larger diameters. And then you can do local things such as surface hardening on particular locations. So for example, if you're going to use a journal bearing, which is the shaft is going to sit inside that journal bearing, or needle bearings that don't have, like, say, an inner raceway and simply lays across that bearing, that shaft, to avoid stress concentrations, you may do some local surface hardening. So that's our first strategy. Our second strategy in figuring out what is the right shaft design for us is layout issues. So by layout, we mean where we're going to put the things on the shaft that are necessary for us. So we see things like a stepped shaft, and these steps are called shoulders, and what they allow us to do is to locate components. So we may put a gear or a pulley here, and every time the manufacturer takes off or puts that gear or pulley back on, it always ends up in exactly the same place because of this shoulder. So the difference between, say, these D's, little diameters and big diameters, that's a ratio that is defined by what we're putting there. So a particular manufacturer for bearings or pulleys or gears, they will define what that ratio should be. In the textbook in Chapter 7 for the Shigley book, you can see some ranges of what is typical for spurs of spur gears of a certain pitch or certain types of bearings. So when you're creating this layout, there's a couple guidelines we'll talk about in a little bit, but we also need to think rationally. So you can't create a shoulder in the middle of your bearing, in the middle of your shaft, because you can't make the diameter of the gear or bearing that's going to fit on there be bigger and then smaller all of a sudden. So you need to think about the layout in such a way that you can locate things from one, insert them and remove them from one side or the other. So that's thinking about the manufacturability of your actual process. And then second of all, thinking about lathe time. So if you have some massive diameter here, this is kind of purposely overly drawn, that means to get down to this diameter here, on the lathe we had to remove all of that material, assuming a constant material on the shaft. So if that's all wasted material, and then you recycle it, and there's some costs associated with that, that can be a waste that you can avoid. So we're going to talk about a couple guidelines, but one of them is basically reducing the amount of extra work you have to do to make that shaft. So let's talk about some layout guidelines. So first of all, shorter is better for a lot of reasons. So the longer the shaft gets, the worse things happen. So we care about bending moments, right? Stress due to bending increases the bigger that bending moment is. So the longer the shaft, the more bending moments you're going to have, the further distance it's going to be traveled. As well as deflection and angle of twist are going to grow significantly more the longer the shaft is. you need to locate as much as possible higher loads near the bearings that are going to support them. So you don't have to put bearings on the outside edges necessarily. You can locate bearings in such a way that they are closer to the actual loads that they need to carry. The second aspect related to that is we only do 2 bearings on a shaft. Trying to locate through more than 2 circles is overly defined on the shaft. So what that results in is that a very high quality is necessary in order to get 3 perfectly aligned circles. So any amount of probabilistic changes in manufacturing or any sort of discrepancies in that will result in many parts not passing your quality control. So that's why we only need to put 2 bearings on a shaft. And then we need to use the minimum fixation for the torque that we have. So if we have a shaft and we need to transmit from one component to another on this shaft, we're going to have some sort of fixation. So we have, say, low torque situations. You can use things like pins or set screws. If you're more moderate torque, then you can use keyways and keys, which means you're going to use an end mill and basically create a groove in your shaft at a particular location, and insert a metal key into both the component and the shaft. And if for higher torque situations, you're going to need to use something like a spline. So if you haven't seen a spline, if you looked at the end of the diameter of the shaft, the spline would be like little spikes that your other outer shaft or outer component is going to fit over. So you want to use the minimum amount of fixation. And the reason is that these increase your stress concentrations. You can also use press fits or tapered fits. These are you physically, with enough force or with a temperature change, push that bearing onto the shaft, and it's dependent on the difference between the hole diameter and the actual diameter of the shaft. But be aware that if you do these press fits and tapered fits, they have low stress concentrations. So you'll have low KFSs or KFs. But in exchange, it becomes hard to disassemble. So if you need to do replacement of the bearings at some point in time, or changing the gears around, you need special tools, and it becomes very difficult and time-consuming and expensive to disassemble. And then finally, we can do things to reduce those stress concentrations that we do have. So for example, if we have a shoulder, there's going to be some stress concentration, and the more we round out that shoulder, the less the stress concentration, as well as we can do things like undercut and remove these materials, and it allows stress to flow. I've obviously significantly overdrawn them here, but those undercuts allow us to have reduced stress concentrations at those locations, and again, often those are driven by say our bearing specifications. All right, the last part is the geometry part. And specifically, we mean that driving diameter. So we have some steps in our shaft, and there's going to be some diameter which is at a critical location, and that's what we want to avoid the static and fatigue failure. So our goal here is to find a diameter that avoids our static and fatigue failure. So if we recall our Goodman equation, modified Goodman, we'd have 1 over n equals our sigma a using von Mises approach, and sigma m over SUT. So if we are looking for diameter, and if you remember the process here, the stress is dependent on diameter, of course, but also the endurance strength had some parameters that are based on the diameter, specifically the Marin factors, as well as the fatigue stress concentrations. So we're going to have to take some guesses here. And our approach is going to be for our endurance strength, you're going to need to do some guess and check for your for the Marin factors. Basically, estimate a close values, probably your KB value somewhere 0.8 range, and come back and fix it later when you know the diameter that you're trying to find, and do that in an iterative process. For the stress, what we don't know is our KTs and KTS, our shear stress and bending moment stress concentrations. These are, of course, dependent on the geometry change, and we don't know the geometry because that's what we're trying to find. So the book has some, again, the textbook has some estimates for ranges for these values. So again, we're going to guess some ranges for both the KT as well as the Q values and the QS's, and come back and fix on your second round. So all of this process with the diameter is going to take at least 2 rounds to do. So if we think about how we load this shaft, say we've got some shaft with bearings and some load on it, and we're transmitting some torque through it. Over time, our bending moment is shaped through that graph, and our torque is a constant while in operation. The stress due to bending at a particular location, typically the outside of the shaft, is fully reversed. The normal stress due to bending. Whereas the shear stress due to torque, no matter where we are on the same, is constant. So what we're going to see here is this affects how we calculate our fluctuating portions of our load. So we're going to have MA and MM and tau A, or torque A and torque M, meaning the amplitude portion of the bending moment, how the bending moment at a particular, how a stress element feels that bending moment at a particular time, and the same thing for torque. And for many situations, the fully reversed means that this is 0, and constant operation means that this is 0. So we really just have those 2 values. But that's not always true, so I'll write it out, the equation, considering both of them being non-zero. Now the other portion that we could have is axial load, right? But the axial portion will often put the shaft in compression. And so since we're concerned about crack growth for fatigue failure, the compression tends to actually relieve some of that stress, that tension stress that we would normally feel from the bending moment. So a conservative approach is basically to ignore the axial portion because it's actually helping to relieve some of the stress. So we're going to design it as if the axial stress isn't there, even with the helical gears that do cause some axial stress. If you're really concerned that the material may buckle, that's another concern if you have a very long shaft. So in all situations, you don't need to ignore the axial force that's going on. But if we're just concerned in a small, normally well-designed shaft, the axial stress is not going to lead to a lot of growth in the stress, growth of the cracks due to stress. So if we were to think about our von Mises form, so let's just look at the amplitude for now, and think in terms of the bending moments that we have and the torques. What we would see is we could say 32 times the amplitude portion of the bending moment, and then this is of course assuming a round solid shaft, whatever stress concentration they have, and then pi d cubed. And of course the other side of that would be the torque part, so we'd have 16 times the torque amplitude and whatever stress concentrations we might have, and pi d cubed. See, it's either squared, and then to the 1/2. So this is for the von Mises form. So as I said before, oftentimes the amplitude portion of the torque is 0, and we only have the mean portion, and then the opposite will be true for the mean von Mises stress. We'll just have the torque and not the bending moment. But what you can see is that we can, using some geometry, basically solve these things for d. So if we went back into von Mises, into the Goodman equation, and solved for d, what we get is this lovely long equation that looks like 16 times whatever fatigue factor of safety we're looking for. So this is how we specify a diameter given factors of safety and material properties. All of that times 1 over the endurance strength, and we will have 4 kf times the amplitude portion of stress squared plus 3 times kfs, the amplitude portion of the torque squared, and then we will have the mean portion. So we need 1 over the ultimate strength times the same formation, except now we are talking about the mean stress and then the shear stress. And then of course the d's were all cubed, so at the end we're going to have 1/3 of all of that, the cubic root of all of that. So that's a tediously long equation, but as I said before, oftentimes the amplitude portion and the mean portion are often 0 here. So we just end up with the mean portion, the amplitude portion of the bending moment, and the mean portion of the torque. So that tells us a diameter that if we want a factor of safety 1 or higher, will allow us, will give us what we need. Now, of course, it's possible to have infinite fatigue life and actually yield, right? There's a portion of the curve where that's possible, especially if we have very high mean loads. So to check for yielding, we use the same von Mises approach of looking for what the maximum stress is. So the maximum von Mises stress, using the same sort of approach, would be 32 mean, the stress concentration, and then the maximum, which is going to be the mean plus the amplitude, over pi, and that diameter we just found, that squared plus 3 times the 16 kfs, and the mean, the torque mean plus the tau plus the torque amplitude over pi d cubed squared, and then 1/2. So this is just the von Mises form kind of worked out so you can see in the same mean moment and mean amplitude, and of course our yield factor of safety is the same as it's always been, so our yielding strength versus our maximum von Mises stress that we just found. So using this approach, what we can do is identify a diameter at a critical location to avoid fatigue failure with some stress factor of safety, and then also check to make sure that given that diameter here, we shouldn't see any yielding. However, if we do this for a particular diameter and stress, we may come up with a fairly small number. And that small number, especially for a long shaft, may actually be not very helpful to us because of the amount of deflection that can occur. So in the next video, we're going to talk about how we look at the deflection concerns. Until next time.